So time for some practice. We're just going to work on integration by parts, trig integrals, and some applications. We're going to jump right into it. Let's go. Number 1. Find the integral log fifth root of x to the fourth plus 1, x cubed. Ugh. Now, before we get too far, I want to make an observation. This part right here, that fifth root part, that looks scary. But you know, we're allowed to rewrite things so that they don't look scary. Absolutely. So let's do that. So notice that we could have said, hey, this is the same as the integral of log of x to the fourth plus 1, and the fifth root means to the 1/5 power, over x cubed dx. Now, what's going to happen here? Well, you see that 1/5 there? That 1/5 power, because we're inside the log, can actually come out. And now it'll look a little bit less scary. So what do we really have? If we say, well, this is really the same as the 1/5, and because it's a constant, you can pull it all the way out in front of the integral, and then we have that log of x to the fourth plus 1 and x cubed. Now, keep in mind, we kind of know coming into these practice problems, we're either thinking integration by parts or trig substitution. Sorry, not trig substitution, trig integrals. It's not trig. So we're thinking integration by parts. With that in mind, let's actually do the following. We're thinking this as log x to the fourth plus 1, and that's this piece, and x to the minus 3. All right, so we have two functions. Now you might say, why not just do a substitution? U equals x to the fourth plus 1, right? And then d would be like an x cubed, except that's not x cubed. It's x to the negative 3. Ooh, good point. All right, well, what can we do? Well, okay, so if we put on our integration by parts hat, and we say, okay, is this a good candidate? And now, one of the challenges, of course, is how do you recognize good candidates? And you kind of go through a process. You say, is this one of our basic functions? No. Is there an easy substitution? No. Because we mentioned, like x to the fourth plus 1 would be, if we had x cubed, we don't. We have x to the negative 3. You know, and as you start going through, like, no. Then you get to the sort of like the bottom. Like, integration by parts is one of the last things we try. Say, well, can we do integration by parts? And oftentimes you'll start to recognize certain things often tend to lead to integration by parts because there's sort of a philosophy. What don't you want to integrate? So if your integral has something that you don't want to integrate, and you say, hey, you know what I could do? Integration by parts says I don't have to integrate it. But I do make a trade, and the trade is instead of doing the integral, I have to differentiate. So now we're like, oh, plan. So this part, the log, we don't like to integrate logs. So we're going to call that our u. And that means everything that's left is the other part, the dv. All right, so let's make some notes here on the side. What is du? Well, because there's a log involved, the derivative of a log is a fraction. And you say, well, what's inside the log? X to the fourth plus 1. Great, put that downstairs. What's the derivative of x to the fourth plus 1? 4x cubed. Great, let's put that upstairs. Okay, wonderful. Feeling good about this so far. And all right, now come to this part. dv. Well, that's dv, so what's v? Well, the nice thing is we wrote it as x to the negative 3, so it's already in its sort of calculus-friendly form. So you would add 1 to the exponent, negative 2, and then you divide by that new exponent. So we end up with v is minus 1/2 x to the negative 2. And we don't need any plus c's at this point. Not for this stage of integration by parts. So, okay, good. Now, what do we have? Well, we're going to have u times v. All right, so we get minus 1/2, and this x to the minus 2, we can write that as an x squared downstairs. So I'm going to go ahead and put it as a fraction. Log x to the fourth plus 1 over x squared. And now don't forget that in front of all this is a 1/5. And we'll catch that later on. Don't forget that. Easy to forget. I almost forgot it. And it's like, wait a second. Oh, don't forget it. Okay, so all right. So here we go. There's our uv. All right, minus the integral v du. Okay, so we have minus 1/2. And then x to minus 2 is 1 over x squared. And then we have a 4. Oh, whoops, for the du, I forgot to write dx. You should get into that habit. Sorry about that. Well, good thing we caught it now. 4x cubed over x to the fourth plus 1 dx. All right, close parentheses. Okay, so let's clean this up. Okay, so what do we have? Well, we have 1/5 times minus 1/2. That's minus 1/10 log x to the fourth plus 1 over x squared. Good. Now, minus minus makes a plus. 1/5 times 1/2, it would make it 1/10. Well, we actually have, though, this 4. So let's be a little bit more careful. So we have 4 divided by 2 is 2, and then times a fifth. So we'll make that as 2/5. All right. And now the integral becomes what? Well, the x squared goes into x cubed, leaving us with an x divided by x to the fourth plus 1 dx. All right. Good. Good. Now, we've traded, right? And that's what integration by parts is. It's a trade. Here's this integral. Let's trade for a different integral. And the goal is that the new integral we trade for is that somehow it's a better model, right? It's going to be a little bit easier for us to work with. That's the goal. It doesn't always work, but when it does, work of art. Beautiful. Okay, so let's start thinking about this. It's definitely easier, at least easier looking. There's no logs. And say, well, we can't be that far away. So what can we do? Well, if we think substitution, x to the fourth plus 1, that would be 4x cubed. Oh, we don't have a 4x cubed. We only have 1x upstairs. But don't worry. There's something else. Do you notice the plus? Ah, yes, that plus sign. That's in a most inconvenient location. But, you know, it reminds me of something. It reminds me of one of my favorite facts. Namely, if you integrate 1 over u squared plus 1 du, the result is arctangent of u. Like, oh, see how there's like plus 1 plus 1? Aha! It's like they wanted it to happen. It's like they wanted it to be there. Now, this might work. This might work. Let's see. In order for it to work, this has to be something squared. So what is x to the fourth in terms of a square? It's x squared squared. So it's like, oh, well, what if we try that? So we set u equal x squared. Then what would du have to be? It would have to be 2x dx. Well, look what we have here. 2x dx. Like it was meant to be. Which means that all of this, for the second integral, we won't forget that integral, we have 1/5 integral of 1 over u squared plus 1 du, which is our arctangent. Oh my gosh. Oh my goodness. Arctangent. I feel like we haven't had enough arctangent yet this semester. So it's good to finally be back. And now we are putting the plus c because we're kind of at the end of integration. So when we're doing the parts, we don't need to worry about the plus c. But when we're like, this is our last integral, we always throw in a plus c. And don't forget, of course, you have to rewrite that in terms of x. So 1/5 arctangent of x squared plus c. All right, well, now that we have all of that, we just put it all together, and we'll be good. So here we go. In the front, minus 1 over 10. Natural log x to the fourth plus 1 over x squared plus 1 over 5 arctangent of x squared and plus c. And there we go. A nice, beautiful answer. All right, good, good. So a couple notes. Be ready for integration by parts. Very frequently happens with logs. And remember, make things easy on yourself. If you have powers inside the log, you can bring them down. Of course, it has to be the whole thing to a power. Like here, we can't bring that 4 down because of that pesky plus. But, you know, we still survived. We still survived. All right, let's keep going. We're given g of 0 is 3, g prime of 0 is negative 1, g double prime of 0 is pi. Ooh, pi. G of 1 is 5, g prime of 1 is 2, and g double prime of 1 is 1. And we're told, find the integral from 0 to 1 of x squared g triple prime. Triple. Third derivative. Oh my gosh. Oh my gosh. Whew. Okay. All right. Now, do we know g? No, we don't. Can we find g? No, we can't. Can we answer the question? Yes. Oh, that's good news. Okay, so how do we go about doing it? Well, if we put on our integration by hats, we say, well, you know, it's really easy to integrate that derivative, right? So we can integrate that g triple prime, keep integrating. Now that x squared, we can keep differentiating. So it's like that works really well. We may have to do it a couple of times, but we're patient people. We don't mind. Lots of practice, right? So let's work through it. All right, so here we go. It's a definite integral, 0 to 1, x squared, g triple prime of x dx. And we say, well, look, the x squared, lovely to differentiate because eventually it goes away. The g triple prime, lovely to integrate because how do you integrate g triple prime? G double prime. What's the integral of g double prime? G prime. You know, and it's just beautiful to integrate. So we're basically being told what to differentiate and what to integrate. So here we go. This is the part we're going to differentiate. This is the part we're going to integrate. So we have du is 2x dx. V is g double prime of x. All right, so here we have. This will be x squared g double prime of x, uv. And don't forget, this is a definite integral, so you need to evaluate. And now we're going to subtract the integral. It's still the same bound, 0 to 1, of v du. And because we know we're going to do the same thing, I'm going to write it in the same sort of format here. So the du, that's our 2x dx, and there is our v g double prime of x. All right, there we go. Okay, well, let's evaluate. Now, when you plug in 0, very easy. You get 0. Good. It doesn't matter what g double prime is 0. Even though g double prime is 0 is pi, doesn't matter. Now, what happens when you plug in 1? You get 1 squared times g double prime of 1. And g double prime of 1 is 1. Okay, so this is equal to 1. That's just this evaluation. Okay, and then, of course, what we have here. 0 to 1, 2x, g double prime of x, dx. All right, progress. Now, we're a little bit simpler integral, right? Not third derivative, second derivative. Not x squared, x. Progress. But of course, we'd always like more. And so we say, okay, do the same thing. U and dv. Once you make a choice about what you call u and what you call dv, if you're going to do it multiple times, you have to be consistent. If I were to say, I changed my mind, I want g double prime of x to be u and 2x to be dv, I'd undo all that good work that we just did. I don't want that. I want to make forward progress. All right, so here we go. What do we have? du 2 dx. And v is g prime of x. Okay, great. Well, let's see what we have. So we have our 1 minus, and now I'm going to use this really cool technology. It came out a few hundred years ago. It's called parenthesis, right? Because whenever you have a minus in front of here, you want to make sure that minus goes through properly. Okay, so we have our uv 2x g prime of x evaluated 0 to 1 minus the integral, still the same bound 0 to 1, of v du. Okay, so 2 g prime of x and dx. All right, and why did I make such a big deal about the parenthesis? Well, because this minus is going to come through, and sometimes you forget about that. See, it's really going to become a plus. So don't forget, be smart. Save your points. Save your points. All right, now let's do some evaluation. When we plug in 0, that x is still going to make it 0. Nice. So we really just have to plug in 1. So we have 1 minus, and then we have 2 times 1 times g prime of 1. So 2 times 1 times g prime of 1 is 4. So that's going to become 1 minus 4. And then we have plus this integral. Okay, so I'll go ahead and write that integral again. The integral is 0 to 1, 2 g prime of x dx. Now, we could do integration by parts here, but we don't have to, because we can integrate it, right? It's saying, hey, here's a derivative. How do you integrate a derivative? You just integrate it, because the 2 is a constant. Just pull it out in front. No problem. We're among friends. And so I say, oh, okay. So that would be 1 minus 4. I guess I could have said that's negative 3, but we'll take care of that in a second. Plus 2 g of x, evaluate that from 0 to 1. Okay, so that's 1 minus 4 plus, okay, so we put 2 times g of 1, which is 2 times 5, that's 10, minus 2 times g of 0, and 2 times g of 0, that's 6. Well, minus 4 minus 6 is minus 10, plus 10. In other words, these last three terms all cancel out, which leaves us with the 1. This is the 1, number 1, value of 1. Nice. And so, really nothing too surprising here. Just carefully work it through, one layer at a time. These problems, I like to think of them, they're like onion problems. They have layers. And just like onions, some tears may be involved. Let a represent a positive integer. If the integral of sine cubed of 2ax dx is 1 over 54 cosine cubed of 2ax minus 1 over 18 cosine of 2ax plus a c, what is the value of a? Okay, well, what can we do? Well, let's integrate, and then let's compare with the integral to what we have. And then we should be able to figure it out. Okay, so we have the integral of sine cubed. Now, when we come to integrating products of sines and cosines, we often look at the exponents. And we say, well, the ideal thing is to see an odd exponent. And we do. Sine cubed. Sine cubed says, aha, I have an odd number of sines. So what we're going to do is when we see an odd exponent, we're going to pull something to the end. And you might say, well, why? Well, let's do that. And so we say, hey, this is really sine squared 2ax sine of 2ax dx. Now, there's sort of a plan. And the plan is, and this is why we pull things off to the end, the plan is to say this piece here is going to become our du. All right, so that's our plan. We need to get there. And how do we get there? Well, we're going to use one of our facts about trig that's so ingrained that 20 years from now, we'll be talking to our grandchildren and we'll talk about, hey, do you remember that one identity? And we're all going to say, you mean that one? Like, yeah, that's the one. And that is, of course, the famous sine squared plus cosine squared equals 1. That's one of the most important identities. We get a lot of mileage out of it. Now, what are we getting out of it here? Well, what it's telling us is that sine squared and cosine squared are really close to each other. And so what we can effectively do is we can do a swap. So that is to say, if I have a sine squared, I can replace it by 1 minus cosine squared. Similarly, if I had a cosine squared, I can replace it by 1 minus sine squared. So even powers of sine, I can replace them with things that look like even powers of cosine and vice versa. So that's why we're doing that. So let's do it. So we're going to replace this sine squared by 1 minus cosine squared. All right, so we have integral 1 minus cosine squared 2ax. And we still have our sine 2ax dx. Now we're ready to make our substitution. So we're going to use our cosine function as the u. U is cosine 2ax. So now what's du? Well, the derivative of cosine is negative sine 2ax. You might say, ooh, you left a big gap there. Well, because we got to do chain rule. Derivative of the inside, derivative of 2ax, 2a. And then don't forget the dx. Now, we just only want the sine 2ax dx. So we only want that part. So we say, okay, let's move that across. All right, that gives us that minus 1 over 2a times du is equal to sine 2ax dx. All right, now we're ready to do our substitution. And so we say, okay, what do we really have now? Well, we have the integral 1 minus u squared. Okay, that's pretty good. And then the sine 2ax dx, there's a minus 1 over 2a and du. And we're like, wow, this is great. Because this is a number, and that's a polynomial. We like these integrals. So there's a minus 1 over 2a. And now we can just integrate u minus 1/3 u cubed. And, of course, throw on a plus c. All right, so the last piece here. We're going to distribute. And we're going to put back in terms of x. So we have minus 1 over 2a times cosine 2ax. And then minus 1 over 2a times minus 1 over 3 plus 1 over 6a. And then it's going to be cosine cubed of 2ax and plus c. Okay, now, good. Let's see, what do we have here? Well, we want to compare. We notice we have a cosine cubed of 2ax. We have a cosine 2ax. So that's good news. Now we could say, okay, so for this to work, we want to have this needs to be 1 over 54. And then this needs to be minus 1 over 18. And now the question, is there a value of a where 6 times a is 54, or where 2 times a is 18? And we say, aha, so 1 over 54 equals 1 over 6a tells us a is 54 over 6, but of course we need to have it be a positive integer. 54 divided by 6 gives us 9. The same way, we have minus 1 over 18 equals minus 1 over 2a. That really tells us a should be 18 over 2, which is 9. You don't have to do both, you just have to do one. But lo and behold, there's the number. That's it. A is 9. Now, is there anything super sophisticated? Not really. Mostly it's just a practice of powers of integrating sine cubed and a little bit of bookkeeping. But that's okay. We still need to practice it. And practice is pretty useful. All right, let's keep going. Find the integral secant cubed y tangent to the fifth y dy. All right, now let's talk strategy. At the core, when we see integrals involving secants and tangents combined, we say, hey, let's recall our trig. And our trig says that if you take secant squared theta, that's tangent squared theta plus 1. Okay, so that's lurking in the background. Now, this is like the last problem where we said, I can trade a sine squared for a cosine squared, and vice versa. So here, I can trade a secant squared for a tangent squared, or vice versa. So, what's the big idea? Well, the idea is to say, well, with that in mind, what we're going to do is we're going to look at two cases. Sometimes we'll do it mentally, but here we'll actually just write it out. Now, case 1 says, what happens if I pull a secant squared off to the end? Okay, so we can have the integral. So if we pull off a secant squared, we're going to have a secant y tangent to the fifth y times secant squared y dy. Okay, that's option number 1. Now, option number 2 says, okay, don't pull off a secant squared, pull off a secant tangent. So if we'd have a secant squared y tangent to the fourth y, secant y tangent y dy. Okay, so we're pulling these off, and we're going to stare at them for a moment. And here's the idea. The idea is to say this part we would want to have BRDU. And similarly here, this part we'd want to have BRDU. Now, how would it work here? Well, in order for your secant squared of y dy to be your du, that means you needed to make a tangent substitution. If I'm making a tangent substitution, I have to replace my secants. Notice our problem. How many secants do you see here? 1. How many do you need? An even number, because even numbers we can replace. Odd we can't. So this is a sad situation. So we can't replace our secant with tangent. We need the square. So this is not going to be the way for us to go. Okay, now let's look here. We don't know automatically that's going to work, but fingers crossed, let's see what's going on. So if we see secant y tangent y dy as our du, we say to ourselves, okay, that means we took the derivative of secant. So we want to replace our tangents. So we come to our tangents and say, do we have the right number of tangents? Right number means tangent to an even exponent. And we see tangent to the fourth. And turns out, true story, 4 is even. We have hope. Oh, yes. Okay, good news, good news. Okay, so, smiley face. We can replace our tangent y with secant y. All right, so now we know we're definitely in our second option, right, of these two. Now, there is technically a third option, which we never want to see, which is secant to an odd power. And if you see secant to an odd power, you're like, no, I thought our teachers loved us. Why are they doing this to us? But, of course, that's not our case here. Now, to help us actually follow through, I am going to do a little bit sort of slow motion here. So I'm going to rewrite this as secant squared y and tangent to the fourth y, just to really emphasize what's going on. I'm going to write this as tangent squared y squared, just to say, aha, here's how we're going to incorporate that tangent squared. And then we have our secant of y, tangent of y, dy. Now, tangent squared becomes secant squared minus 1. Okay, so we have integral secant squared y times secant squared y minus 1 quantity squared secant y tangent y dy. All right, now the magic. Here we go. We did a lot of work here so that we could say, let's make our substitution secant of y so that the derivative of secant is secant tangent and throw dy. Okay, now, good. So, our integral, we have integral u squared times u squared minus 1 squared, and then du. Algebra. Wonderful algebra. So if you square that out, that would be u to the 4th minus 2u squared plus 1 du, and then you distribute the u squared through. So that would be u to the 6th minus 2u to the 4th plus u squared du. So again, we're just doing algebra. We can do expansion. That's pretty straightforward. And now, term by term, add 1 to the exponent and divide. So it's 1/7 u to the 7th minus 2/5 u to the 5th plus 1/3 u to the 3rd plus c. Now, is that our answer? No. We introduced u, so we have to go back to y. We say, okay, well, that's no problem. We know what y is. Sorry, we know what u is. U is secant of y. And we say, okay, so now everywhere you see a u, put a secant. So our real answer, we'll put it over here, 1/7 secant to the 7th of y minus 2/5 secant to the 5th of y plus 1/3 secant cubed of y plus c. And there we go. Whew! Wow! What an answer! That's all right. That's the process, right? We saw it work. Just be patient, work it through, and yeah. So whenever you see secant tangents, this step is often done mentally, but it doesn't hurt to just write down what are my two options and what can I swap. Sometimes you can swap both. Sometimes you can only swap one. In this case, it was forced on us, and we just followed it along. Life was good. Life is wonderful. Let's keep going. Applying integration by parts once to the integral 8x to the n minus 1 e to the 6x dx produces the reduction formula 8x to the n minus 1 e to the 6x dx is px to the n minus 1 e to the 8x over q minus p over q n minus 1 integral x to the n minus 2 e to the 6x dx, where p and q are integers. When fully reduced, what are the values of p and q? Okay, so let's go through and talk about two pieces here. What does it mean when it says reduction formula? And then, what does it mean when it says fully reduced? They actually mean slightly different things. Okay, so let's start with the reduction formula. So when you're solving a problem, one of the classic strategies is to say, let me take my hard problem and turn it into a less hard problem. In other words, make it a bit easier, reduce the difficulty. And so when it talks about a reduction formula, what it's basically saying is, I want to swap out a integral for a slightly easier integral. So that's the reduction formula. In other words, it's saying, here's a challenging integral in general. I can swap an integral out for a slightly easier integral. Reduction of difficulty. When it comes to here and it says fully reduced, What it means is when you look at P and Q are here as ratios. And so fully reduced says remove any common factors. So I wouldn't leave it as like 2 over 4. I would write it as 1 over 2. Right? So just clean it up as much as you possibly can. That's what fully reduced means. Okay, so what's our idea? How are we going to approach it? Well, we know that this came from doing integration by parts. And so we're going to do integration by parts and actually derive the reduction formula and then see what it tells us it should be. Now, when we do integration by parts, we have to figure out which part are we integrating, which part are we differentiating. But it's not so hard here because we look at this and say, okay, what happened to the power of x? Now notice this power of x is to the n minus 1. Here it's to the n minus 2. And so did the power go down, took a derivative, or did it go up? Integrate. It went down. So the x is the part that's going to be the u. That's the part we're going to take a derivative of. And then the exponential, that's the part we're going to integrate. All right, so with that in mind, let's get to work. So we'll write down our generic formula here. Hello, generic formula. Okay. And we have our, we'll go ahead and throw the 8 on one of them. We'll just do it on the first one. Here's our u. Here's our dv. So the derivative, well, 8, the power n minus 1 comes down, x to the power n minus 2 dx. And, v, integral of e to the 6x is e to the 6x, but then you have to account for that 6, so you divide by 6, 1, 6. Okay, so according to the rules for integration by parts, what do? Well, we're going to take u times v, so we have 8 x to the n minus 1 times 1, 6 e to the 6x. There's a typo here. Just pretend like I didn't have that typo in the problem. That should have been a 6. Shh. All right. 1, 6 e to the 6x. Good. And now minus integral v du. Okay, so that's 1, 6 e to the 6x times 8 times n minus 1 x to the power n minus 2 dx. All right, well, okay, 8 divided by 6. What is that? Well, take out the common factors. That's 4 over 3. And then you have x to the n minus 1, e to the 6x. And at this point, you're like, p, q. That's right. But we'll go ahead and finish writing it down. Again, we have 8 over 6, so we can pull that out. 4 over 3. N minus 1 is common factor. And integral of x to the power n minus 2, e to the 6x dx. Great. Wonderful. Wonderful. All right. Well, now we really just are comparing. And we say, hey, look, this piece is matching up with here. And so at this point, there's really not much else to say other than, hey, we did what you did, and these are the numbers that we got. So P should be 4, and Q should be 3. And that is our answer. And there we go. Nice! Ha-ha! Huzzah! Huzzah! And let's keep going. Find the integral of 4 arctangent cubed root of x dx. Now, everybody loves a good arctangent problem, and I hope we're all going to like this one too. And our first reaction is like, oh, this is really messy. And we could just try to jump straight into doing integration by parts, and sometimes it doesn't hurt to do that. But I like to clean it up a little bit. And because I see I have a function in a function, and I want to see if I can't somehow make it a little bit simpler to digest. So let's do a substitution before we get going. And keep in mind that we suspect integration by parts will be involved. Let's not use the letter U because we're so used to using UdV when we do integration by parts. So let's use a different letter. And how about Y? Works just as well. Okay, so idea. Let's first clean it up. And we say, I see function in a function. So think substitution. So let's let Y equal x to the 1/3. So, all right, well, that's pretty good. That'll make the inside of arctangent very simple. But remember, I can't just replace the inside. I got to replace all of the places. So all the x's have to be replaced. So right now we're at 4 arctangent of y. But the question is, what do you do about the dx? Now, there's a few ways to do this, but I'm going to try to do it a way that is easy for me to do computationally. I have y as the cube root of x. Because this is like a x to a cubed root or some sort of a root, before I take derivatives, we can use exponentiation. So we can say, well, that's really the same as y cubed equals x. Now take the derivative. 3y squared dy equals dx. Yes? It's true. It's true. And so what would that become? The dx becomes 3y squared dy. All right. Good. Good. Now, you might be saying, you cheated. You can't do that. That's not going to work. Okay, so let's talk about what other people would normally do in this scenario. So I have a different color here. You'd say, no. See, what you should have done is you should have taken the derivative, right? dy is 1/3 x to negative 2/3 dx. That's what you should have done. But okay, let's see what happens. Let's get the dx by itself. So dx would then become 3 x to the 2/3 dy. What can I do with x to the 2/3? Well, x to the 1/3 is y. So what is x to the 2/3? Well, it's like 2x to the 1/3, or it's 2 y's. So this is the same as y squared dy. So it works either way, but I like this method first just because it makes it easier. And it sort of goes back, I've said this many times, but fractions are tough, and you have to be careful. It's easy to make mistakes with fractions. All right, so now we have our new integral. So we're going to work with this integral and see how far we get. And it certainly feels a little bit more straightforward. What can we do here? Well, one thing we can certainly do is we can write the 4 and 3 together. In fact, those are constants, so we might as well pull them out. 12. And, okay, we have arctangent of y squared dy. Now, thinking integration by parts. Is there something that we want to integrate? Is there something we want to differentiate? And I would say arctangent of y, I love you. I'm a big fan. I've seen all your best hits, but I don't want to integrate you. So with that in mind, let's differentiate it. So I say, okay, arctangent of y, we'll have that be our u. Y squared dy, that would be our dv. Now I kind of regret moving the 3 and putting it in with the 4. Well, that's okay. Life is like that. You never know where you're going. All right, so let's just see what's going to happen. So du, root of arctangent, 1/1 plus y squared dy. And v, integrate y squared, 1/3 y cubed. Ah, okay. This is feeling pretty good. Yeah, we're making progress. Okay, so what do we have? Well, don't forget that 12 in the front. So 12 uv. So we'll have 1/3 third y cubed arctangent of y. All right, good, good, good. Minus the 12, don't forget the 12, still there, and integral v du. So integral of 1/3 y cubed times 1 over 1 plus y squared dy. All right. Well, we can clean this up. So we have really 4y cubed arctangent of y, and then minus 4 integral of y cubed over 1 plus y squared. Now, the question is what to do about this y cubed over 1 plus y squared. And I will say I'm going to sort of wave my hands a little bit at the next step. And that's because what I'm about to do really is kind of a preview of partial fractions. I'm kind of hiding a long division, but it's a small thing I'm hiding. So don't get too stressed by what I'm about to do. I'm going to add 0. You're like, whoa, not the 0, Steve. Yes, that 0. People are probably like, what 0? Well, I'm going to add a very well-chosen 0. So I'm going to add y and subtract y. And you're like, oh, that's amazing. How'd you do that? Or probably you're thinking more like, what? Why did you do that? Okay, so let's rewrite it, and then I think it'll become more clear about what's going to happen. Now, of course, adding and subtracting y, it hasn't changed anything. It's like adding 0. But the goal was to add a well-chosen 0. So, in particular, what we're going to think of is we're going to think of the first two terms as coming together. So we have y cubed plus y, and then we have the second term by itself. And the reason that what we're going to do next is so nice is see that minus sign? That's the good kind of minus sign. It's the one that lets us pull it apart. So you can think of this y cubed plus y as really y times 1 plus y squared divided by 1 plus y squared. Okay, that's the y cubed plus y over 1 plus y squared. And then we have minus y over 1 plus y squared. Okay, and here, now it's like, oh, so it was done to clean things up. All right, so we can do a little zoop, zoop. You don't have to make the noise when you're doing the quiz, but you can do it in your head. Make a little zoop, zoop sound upstairs. It's always fun, right? We should have fun. Tests should be fun. Okay, so let's see. Integral of y, yeah, we can do that. That's no problem. So we have 4y cubed arctangent of y, and then minus 4 times 1/2 y squared. Okay, plus 4 integral y over 1 plus y squared. Okay, right, because remember that we'll distribute through. Now we have that last thing. How do you integrate y over 1 plus y squared? Well, it's not arctangent. Arctangent is just 1 over 1 plus y squared, but it's not far off, right? So we say, okay, well, what can you do? Try substitution. If you let u equal 1 plus y squared, what's du? 2y dy. Or y dy is 1/2 du. And so, if we just look at this piece right here, this would become the integral of 1/2 times 1 over u du. Right, the 1/2 coming from the y dy. And then the 1 over u is the 1 over 1 plus y squared, which is 1/2 log u plus c. Okay, so that says we now have the following. 4y cubed arctangent of y. 4 times a half makes minus 2y squared. 4 times another half makes a plus 2 log u. But u is 1 plus y squared. So 1 plus y squared plus c. Ah, done. Done. Except we're not. Wait, what? We're not done? But we worked so hard! But what are we missing? No, we got the plus c. It wasn't that. We started with x. So if you start with x, it's an indefinite integral. You have to end with x. So you say, oh, okay. Well, what is x? Well, wherever you see a y, put x to 1/3. So in particular, what's y cubed? Well, we actually wrote it down. It's x. So we say, oh, so really our answer is 4x arctangent of x to 1/3. Okay, that's that. Minus 2y squared. Well, y squared, well, x to 2/3. So minus 2x to the 2/3. Then plus 2 natural log of 1 plus y squared x to the 2/3. And plus c. So that's our real final answer. Whew! We did it! We made it! Huzzah! Okay, there we go. There we go. So, yeah, I really like to substitute when I see some complicated function in a function at the beginning, and it can make integration by parts a little bit easier. Doesn't always have to be done, but I'm a big fan of making things a little bit more transparent, and so that's the reason I like to do that. I think perhaps the hardest part of this is it just sort of seems to come out of nowhere, but it doesn't really come out of nowhere. What we really did was long division. We will talk about that more when we talk about partial fractions. So if it seems weird, don't worry. We will talk about it more, and then it'll be like, okay, it was really just long division. But other than that, yeah, be patient, work it out. You can do it. You can do it. Find the average value of the function h of x, which is 1 over the square root of 1 minus cosine 4x, over the interval pi over 8 to pi over 4. Okay, well, this is going to be interesting. Now, I'm going to add some warnings here. This may not feel like the right way to do this problem, but it is probably the better way to do this. One of the things that you might say is like, ooh, let me use conjugation. And if there was a square root of 1 minus cosine 4x upstairs, I would be 100% behind you. I'd be like, yeah, let's do it. Woo! We're in for a ride. When it's downstairs, it's not a good approach. The problem is that you can do multiply top and bottom by conjugation, which would be square root of 1 plus cosine 4x. But now the sign is downstairs. And then how do you migrate it upstairs? And then how do you replace it in a friendly way? It leads to lots of headaches. Okay, so when it's downstairs, it's like, what can you do? Now, it turns out that hope is not lost, because there is something that looks like a 1 plus or minus a cosine and looks like a square. So let's remind ourselves of, well, let's do it down here in the corner. So we'll start with our power reduction. And if we do that, that says cosine squared of x is 1/2 times 1 plus cosine of 2x. And sine squared of x is 1/2 times 1 minus cosine of 2x. Okay, so that's power reduction. Now, what does it say? Well, and keep in mind, there's something that you always have to keep in the back of your head. is that whenever you have square roots, you kind of are hoping, can I make the inside look like a square? Because if I can make the inside look like a square, that's a victory. We win. You say, well, this 1 minus cosine kind of looks like a sine squared. And so it's like, ooh, idea. So what we can say is, hey, this 1 minus cosine of 2x is really 2 sine squared of x. And in a very similar way, 1 plus cosine of 2x looks like 2 cosine, 2, I know how to write 2 cosine squared of x. All right, so what does that allow us to do? Well, it allows us to rewrite. Okay, so we're going to do that. And a lot of math is just rewriting. And really, you could argue simplifying is just a fancy way of saying rewriting, and just so it's a little bit easier. So, okay, so let's be careful here, because you might notice we don't have 2x, we have 4x. And here's the key to observe. Whatever this angle is, it's twice that angle. So, if we want to replace the inside, that'd be 1 over, and the square root of 2 sine squared of, what's the angle? 2x, right? Because this angle should be double what's in there. So if I want it to be double, that should be a 2x. All right, well, so this gives us square root of 2. So I'll put this as 1 over square root of 2 and 1 over sine. Now, here is a little bit of some unfortunate news. 1 over sine leads us to a function which we don't often play with, which is cosecant. So, but that's okay. We'll go ahead and just mention that. All right, now how do you work with cosecants? Similarly, how do you work with cotangents? And sort of the punchline is, as far as calculus is concerned, they'll look the same, but whatever's true for the part without the co, add the co and toss in a minus. And that's it. If you remember that, then you're good to go. Okay, now, that was all about rewriting it in a simpler, because there's cosecant. Secant would have been nicer, but all right. We have to remind ourselves, hey, average value, what's that? Okay, so that's something that we learned about in Calc 1. Calc 1. we were so innocent back then. So how does one find average value? So there's a particular expression. So average value of f of x for a less than or equal to x less than or equal to b became, you divide by 1 over b minus a. So we're thinking of going on the interval from a to b. So it's the length of that interval, right? That's that, b minus a, integral a to b of the function f of x. Okay, so that's the average value. So for us, what are we going to be doing? Well, so we're going to have 1 over pi over 4 subtract pi over 8. Okay, we have our a, b, b minus a. Integral from pi over 8 to pi over 4 of our function. And we'll use the one that we've cleaned up. 1 over square root of 2 cosecant 2x. Okay. Now pi over 4 subtract pi over 8. This is just pi over 8. And then just remember, we're going to flip it upside down. So we really have our constant will be 8, a pi, and a square root of 2. Ha! That's cool. We haven't even integrated anything. And we're all like, this is a fun number, whatever it turns out to be. Okay, so how do you integrate cosecant? So again, remember what I said a minute ago. Think about integrating secant, add a minus, and put in cos. So we're going to have a minus sign, and then we're going to have a log. Now, the integral of secant is secant plus tangent inside the log. So we're going to have integral of cosecant is cosecant and cotangent. Okay, now, is this our integral? And why not? What did I forget? I forgot something. I forgot two things. Plus c, right? Ha ha ha. Okay. No, not plus c. Because what? It's a definite integral. So you're like, oh, you forgot to evaluate. Okay, good. All right. All right, good. Now, is there anything else we forgot? There's one more thing. What is it? The 2. You got to account for that 2 on the inside. How do you account for it? Times by a half. Okay. So, we're going all over the page here. But, all right. We'll go ahead and divide 8 by 2. So that leaves us with 4 pi square root of 2. Okay, so now we're going to put in pi fourths. So minus log cosecant of pi over 4 plus cotangent. Sorry, not pi over 4. 2 times pi over 4. Pi over 2. Slow down. Don't overthink things. Just think them, right? So minus log, plug in pi over 4. Minus makes plus log, plug in pi over 8. And now you get 2 times pi over 8 is pi over 4. Cosecant pi over 4 plus cotangent pi over 4. Okay. All right, we're almost there, but we should evaluate. Now, what is cotangent of pi over 2? Well, it's sine, cotangent's cosine over sine. Cosine pi over 2 is 0. So this is 0. What about cosecant pi over 2? Well, that's 1 over sine. 1 over sine pi over 2 is 1 over 1. So this is 1. So it's log of 1, which is 0. Oh, all that work to say that term drops out. Okay, now pi over 4. Cotangent of pi over 4. Well, that's cosine pi over 4 divided by sine pi over 4. It's also 1 over tangent of pi over 4. So this is 1. How about cosecant pi over 4? Well, that is 1 over square root of 2 over 2. But if you flip that over, you get 2 over square root of 2, which is also known as square root of 2. And so, if we put this all together, what do we end up with? Well, we end up with the 4 natural log square root of 2 plus 1 divided by pi square root of 2. Whoosh. There we go. All right. Wow. What a strange answer. But that's okay. The process works. And so on this problem, of course, make sure you remember, how do you find average value? 1 over b minus a, integral a to b, f of x dx. How do you handle square roots? Well, conjugates are nice, but really only if you have that square root upstairs. Downstairs, it can lead to challenges. And so in our case, we said, let's modify the power reduction so that we can get the inside to look like a square. And then we were just very, very careful. You can do this. And I oftentimes, when I do these problems, I'm picking sort of harder versions of them. And so that's why I ended up with the cosecant. Don't panic. Even if you get a cosecant, you can handle it. But I suspect you probably have something nicer, like a secant. Secants. What a beautiful function. All right. Well, we have a few more to go. Let's keep going. A parametric curve is defined by x of t as the integral 0 to t sine cubed tau cosine cubed tau d tau. And y of t is cosine t, where t goes from 0 to pi over 2. Find the area under this curve and above the x-axis. Okay. Interesting. All right, now how do you go about such a problem? Well, we want to find the area under this curve and above the x-axis. So what we should think of is the following. We should say, well, I don't know exactly where it is. I mean, at time 0, we see that x is 0 and y is 1. Yeah, okay, so it's doing something. And at time pi over 2, cosine of pi over 2 is 0. And that is some number I don't know. Okay, so it's doing this. And I'm pretty confident it goes there. And I'll explain why I'm very confident it actually does do that. Okay, so there's our picture of our curve. And now we say we want the area under the curve and above the x-axis. So in other words, we're after this area. Now, how do we do it? Well, we channel our inner like applications and say, well, if you're after area, what would you do? You would break things up into rectangles. Say, oh, all right, I'm a big fan of rectangles. You say, okay, what's one rectangle? Well, the area of a rectangle, so a single vertical slice, well, you have your height, that's your y of t. Then you have your width. Now here's where things get a little bit dicey. It's not t, because this is not the ty, this is xy. So it's a small change in x. How do we find that small change in x? Well, we can take the rate of change of x times the amount of change in the input. So that's our x prime of t dt. All right, now that's the area of one slice. So how do we find all the slices? You add them all up, and so we get that the total area is adding up from A to B of our y of t, x prime of t, dt. And when I say A and B, I'm referring to the ones for time. All right, good. Now, when you see it, it's like, okay, that seems pretty reasonable. There is a small catch in that you have to sort of check the sign for x prime and say, well, is that positive or negative? Because there could be an orientation, and if there's an orientation, you have to fix it. But let's find x prime because we're going to need it. And we say, well, we could first integrate sine cubed cosine cubed, actually find x of t explicitly, and then take the derivative. But that sounds like work. We don't want to do work. We want to have fun. Yes? Fun, right? It's all about the fun. And you're probably thinking, oh, Steve, he's gone mental. Oh, yes, fundamental. It's the fundamental theorem of calculus. Okay, all right, so x prime of t. The way we're going to define that is to say, hey, you know, it's the derivative of an integral. So x prime of t is the derivative of the integral, 0 to t, sine cubed tau, cosine cubed tau, d tau, which makes this sine cubed of t, cosine cubed of t. Now, I'm going to jump back to something I brought up a few minutes ago. Are we confident we're moving in this direction? Well, what happens between 0 and pi halves? Sine and cosine are both positive, meaning x prime is positive, means we are indeed going in the positive increasing values of x. Okay, so all of this work is to say the following. We need to compute the integral, So here's the area. 0 to pi over 2, a to b. Y of t is a cosine t. And then we have our sine cubed t cosine cubed t dt. Okay, so it's powers of sines and cosines. And, well, if we've lived a good life, hopefully one of these will be an odd power. So sine cubed cosine to the fourth. Oh, one of these is an odd power. Yes, yes, that's a good news for us. Woohoo! Now, remember, when one of them is an odd power, we're going to pull that odd one off to the end. Okay, so this becomes integral 0 to pi over 2. We're going to have a sine squared cosine to the fourth times sine dt. And what's happening is that this sine is going to become our du. So we need to change everything into cosine. So in particular, we say, I have this even power of sine. That's why we pulled off the sine, so that we're left with an even power of sine. I can replace even powers of sine in terms of even powers of cosine. And in this case, it's fairly straightforward. This is 1 minus cosine squared of t. All right, so we are now at the following. Integral 0 to pi over 2. We have 1 minus cosine squared of t times cosine to the fourth of t times sine of t dt. And with all our groundwork laid, we're now ready to do our substitution. So we're going to let u equal cosine. And when we do that, the derivative of cosine will be negative sine t dt. Using our fancy marker technology, minus du is sine t dt. So let's update. Plug in our bounds. Cosine of 0, 1. Cosine of pi halves, 0. Then we get 1 minus u squared, u to the fourth, and then sine t become a minus 1 du. Or we can use the minus in connection with our bounds, right? So we can say, hey, I can use that to reorder the bounds so they look like normal bounds. And when I say normal, we really like to think going 0 to 1. Okay, so this is the same as the integral 0 to 1. And, all right, that takes care of that minus. Distribute through u to the fourth minus u to the sixth. U to the fourth minus u to the sixth du. Okay, and so that's 1/5 u to the fifth minus 1/7 u to the 7th. Evaluate 0 to 1. We're almost there. Now notice, we don't have to go back to sines and cosines. It's a definite integral. When we have definite integral, update your bounds. You always move forward. You don't have to go back. And so that's good news for us. Other great news, it's really easy to plug in 0. And it's pretty easy to plug in 1 too. So we have 1/5 minus 1/7. Well, that's the same as 7 over 35. So multiply by 7 over 7. Minus 5 over 35. Multiply by 5 over 5. So you get common denominator, leaving us with our final answer of 2. Divide by 35. And that's how much area there is. Turns out, not a lot. And that's okay. That's all right. And there we go. Okay. Woohoo! We did it. We made it. And there was a couple of fun things here. The fundamental theorem of calculus, we had to use that. Had to remember how to take areas with parametric curves. So you got your y, x prime. Yeah, lots of little pieces. But, It's time for us to start putting things together. So, all right, well, almost there. A few more problems. We can do it. Let's hang in there. Let's make it. Find the area of the region bounded by the polar curve, r equals 4 sine squared theta cosine theta, and between 0 and pi thirds, residing in the first quadrant. Okay, so some good news. We know we're in polar, okay, because it says polar. We can pick up the hints. No matter how subtle they may be, we can pick up hints. We also know we're after area. So good news is we have a formula for area for polar. So we'll get to that in a moment. Now, there's not a picture here, but we can get a quick rough sketch. So we know we're in the first quadrant. We know we're between theta equals 0, which is the same as the positive x-axis. Theta equals pi over 3 is roughly 60 degrees. So let's say this is theta equals pi over 3. And then we have the curve, and I'm not sure exactly what it looks like, but we don't have to know exactly to get a feel. We can see, for instance, when you plug in 0, you get 4 times 0 times 1. So that's 0. So it starts at 0 at the origin, and then it probably comes out and does something. So let's say that's what it does. I don't know if that's it. I don't have to know exactly. But we say, okay, so we're after this area. All right. So there we go. That's our goal. What's the area of this piece? Well, what can we do? To make progress, we say, well, we need the area formula for polar. And so we go and we look that up. And it says, if you want area in polar, it's the adding up from alpha to beta of 1/2. Then you have the outer function squared minus the inner function squared d theta. Now for us, when we talk about inner function, outer function, everything always comes back to the origin. So there's actually just the outer function. The inner function is 0. So we say, oh, cool. That makes things simple. And alpha and beta are given to us, also making things simple. All right, well, this is looking like there's not going to be any surprises. So let's go ahead and write things down. We have 0 to pi over 3 of 1/2, and we just need to square that. 4 sine squared theta cosine theta d theta. Okay. And, whoops, I said square it, so we better square it. There we go. Nice. Nice. Okay. All right. Well, let's do it. We can do it. We can do it. Our powers combined. Me and you together, we're going to make it through it. I believe in us. I believe in us. Well, we can square the 4. That gives us 16. And then times by half gives us 8. Okay. All right. That's good news. So this is really 8 integral 0 to pi over 3 of, and now we have to square the pieces. So sine squared squared, sine to the 4th, cosine squared d theta. Okay, now we're going to do a little bit of work on the side here. So what's going on? Well, we have powers of sines and cosines, but unlike the last problem, where we could say, one of them is odd, ho, 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 and off to the races, and we were so excited. We don't have that here. Everything's even. But that's okay. We still have a plan. And so what we do is we go and say, let's look at our power reduction rules. All 3 of them. And you're probably thinking, 3? I thought there was just 2. No, there's 3. Okay, so let's remind ourselves. We have cosine squared theta. That's 1/2, 1 plus cosine of 2 theta. We have sine squared of theta, and that's 1/2, 1 minus cosine 2 theta. And now the third one. Cosine theta times sine theta is 1/2 sine of 2 theta. So those are our three power reduction. And power reduction in the sense of we're going to reduce the exponent attached to the trig function. Now here, there's two trig functions versus one trig functions. So we're reducing the power, but the trade-off is we're bumping up the inside. And so, in case you're wondering, where is this third one written down? This is the double angle formula. Now, while they're all wonderful, when possible, and as much as possible, use that one. And the reason why we love to use that one is there's no plus or minus. Pluses and minuses are dangerous because it leads to algebra. And algebra can, if we're not careful, lead to mistakes. Now, of course, I know we would double check and triple check, but even the best double checking, triple checking, occasionally mistakes sneak through. So when we can, there's it's sort of a nice mindset to say, let's be kind to ourselves. Because we love ourselves, we want ourselves to succeed. So we want to set ourselves up for success. All right. Now, with that in mind, we say, if we're going to use this as much as possible, what is as much as possible? Well, we're going to grab 2 sines and 2 cosines. So essentially, look at the smaller of the powers. Say, okay, great, we can do that. So we're going to think of this as 8 integral 0 to pi over 3. And we're going to have our sine theta cosine theta quantity squared. And then what's left? It'll only be sines or only be cosines. In this case, it's sines. Sine squared. All right. Now, our big aha. Use power reduction. So we should switch colors. We'll go green. All right, green it is. So sine theta cosine theta. This part is going to be the 1/2 sine 2 theta. And remember, that's being squared. Don't forget to square that. Sine squared theta, that's 1/2 1 minus cosine 2 theta. Okay, so what does this all become? Well, let's start with our constant. We have a half, that can come out. And here we have a half squared. So it's a half and a half and a half, or 1/8. There's already an 8 there. Constants are gone. Nice. The constants are gone. Well, maybe it's not worthy of a song, but that's kind of clean. We like it when things work out nicely, don't we? I like it. So we're at 0 to pi over 3. And now let's distribute. We have sine squared of 2 theta minus sine squared 2 theta times cosine 2 theta. Okay. Now, moment of truth. What are we going to do? Well, the answer is we're going to do these in a slightly different way. This part right here, we have one of the terms is odd, the cosine. So that's pretty good. This first part, we only have even. So, do it again. Power reduction a second time. All right. Well, okay. So, let's think about breaking this up into 2 integrals. 0 to pi over 3. The sine squared 2 theta would become 1/2 1 minus cosine. And I'm dramatically pausing because this is a place where I know I make mistakes. And so whenever I make a lot of mistakes, I always I'm going to be a dramatic pause. Got to remember to double what you had. So we didn't start with theta, we started with 2 theta. So we're not going to end with 2 theta, we're going to end with double 2 theta. 4 theta. 4 theta. Okay, now that's the first one. All right, and we'll work on that in a second. And we're going to do the second one slightly differently, so we'll just pull it off. 0 to pi over 3. sine squared 2 theta cosine 2 theta d theta. Okay. Well, let's work on these integrals. So here we're going to have 1/2 times theta minus, and the integral of cosine is positive sine, so sine 4 theta, and then you have to multiply by a 1/4. And we're going to evaluate from 0 to pi over 3. On the other hand, for this second integral, we're going to take advantage of what we have. So if we let u equal sine of 2 theta, then du is 2 cosine 2 theta d theta, or using our fancy markers, 1/2 du is cosine 2 theta d theta, which means that this becomes, on the end, the integral of 1/2, from that 1/2 right there, u squared from the sine squared du. But what are the bounds? Okay, good. Well, let's plug in the bounds. 0, sine of 0 is 0. That's cool. How about sine of 2 pi thirds? Well, that we should figure out. Okay, so if we come to our unit circle, we say, all right, 60 degrees is roughly here. That's pi over 3. To get to 2 pi over 3, you can go pi back pi over 3. So 2 pi thirds is the mirror. So in other words, it's exactly across. So if I know what sine of pi over 3 is, sine of 2 pi over 3 has the exact same value. Well, we do know what sine of pi over 3 is, because there's like a table on our formula sheet. And that turns out it has the value of square root of 3 over 2. Okay, so this last part now, we're going to integrate, don't forget the minus, integral of 1/2 u squared, 1/6 u to the 6. U cubed. Sorry, the 1/6 threw me off. 1/6 u cubed. Okay, and then evaluate 0 to square root of 3 over 2. All right, well, we're getting close to the end, which is good, because we're also getting close to running out of space on our page. Okay, all right. Good news. Plug in 0, plug in 0, plug in 0. It's all 0. Whew! Which means we just need to plug in our upper bounds. So we have 1/2 times pi over 3, pi over 6, minus 1/2 times 1/4 is 1/8, sine of 4 pi over 3. Okay, so where is 4 pi over 3? Well, we've already done pi over 3. Here's 2 pi over 3. 4 pi over 3 is to go pi plus another pi over 3. And so it's exactly opposite. So if I know what my sine is over here, then take the negative over there. And we know what the sine is over here. So that says that if I take the negative of that, it's negative square root of 3 over 2. Okay. So that's sine of 4 pi thirds. Minus 1/6 times square root of 3 over 2 cubed. So that's square root of 3 over 2 times square root of 3 over 2 times square root of 3 over 2. Oh, boy. All right. Does anything nice happen? Well, if I take 2 of those square root of 3's together, then that makes a 3, and then I can divide. And because 6 is divisible by 3. And, okay, so that's good. And notice here I have a minus, and a minus makes that a plus. And so what do we have here? We really have pi over 6 plus square root of 3 over 16. And here there's a minus, there's a square root of 3 left upstairs, and 1, 2, 3, 4, 2 to the 4th, 16. Oh my gosh! What? That is so cool! That is so cool! Wow! They cancel. Okay, which tells us what? Tells us our final answer is pi over 6. So let's write it really big so we can celebrate. Look, it's pi over 6. What a beautiful, pretty answer. Nice. Oh, wow, that was so cool. Okay, so anyways, yeah, that's the process, right? And so not too many surprises on this one. We knew we were polar, so 1/2 radius squared, which led us down to saying, oh, deal with even powers, practice power reduction, and then just be careful. And sometimes you have to do power reduction multiple times. Sometimes you might do something on this piece, do something else on that part. But in the end, we got our answer. And our answer was nice. Will your answer be nice? I don't know. It's a different problem. Sometimes different problems choose not convenient numbers, but that's okay. We know the process. The process is the important thing. All right. Good. Good. Our final problem. Woohoo! Okay, let's do it. Let's do it. The region bounded by y equals x squared log of x squared. Now be careful. The square is outside the log. So that too does not come down. So pay attention to where your powers fall in. Is it a power inside the log or outside the log? Because it makes a difference. Anyways, back to our regularly scheduled problem. So our region is bounded by our function and the x-axis on the interval 1 to e. And it's rotated about the y-axis. Find the volume of the resulting solid. Okay, so we can get a quick sketch here. And we don't have to be super precise. Let's say this is 1. You can plug in 1, and log of 1 is 0. So, okay, starts there. And we're going to go to e. And log of e is 1. Well, that's convenient. And so we're going to jump up to e squared. And we don't need to know that, but okay. So we have this region. It's bounded by the function and the x-axis. Okay, so in other words, this is our region. Okay, cool. Now, where are we spinning? We are rotating about the y-axis. All right, so y-axis is here. So that's how we're spinning. And now, volume. Now, when it comes to volume, there's two options, right? There's shell method, there's washer method. Which one are we, and how do we know? Well, in some sense, we can be either, but usually the problem is presented in a way that we want one over the other. Which one here? Well, when we look at our function, it's a function of x. Okay, so what does that say? If it's a function of x, we're thinking of slicing vertically, up and down. So there's a typical slice. And why do we slice up and down? Because small change in x means you have thin, skinny rectangles. Now, using a pen or pencil, whatever you have, if this is your slice and you spin it, what shape are you making? What's the shape? If you spin it around, you are forming a cylinder. So, aha, cool. We are going to be going with shell method. Okay. Now, what do? Well, we look up what's the formula for shell method. And conveniently enough, we have it available. It's nice that we have it as a reference. We are adding up our pieces, A to B. We have 2 pi. Then we have our radius, our height, and our width. Okay, so we just have to sort of put all those pieces together. Now, some pieces are easier to identify than others, so let's get some low-hanging fruit. A and B, that's pretty quick. Those are our bounds, 1 to E. 2 pi is 2 pi. Now, for radius, what you do is you have your slice, and you say, well, how far is my slice? And you think of your slice as being at some arbitrary x. How far is it from my arbitrary x value to the axis? And the answer is x. Now, we could have been spinning around a line like -1, then we'd have to adjust it, but around axes it tends to be very simple. Now, what about the height? The height. Well, the height is this segment here, which comes from the function. So, this is x squared log of x squared. And the width, well, that's just the small piece here, and that is your dx. All right, so there we go. Those are all our pieces. We figured it out, and now we're just going to put it all together and see what do we have. Okay, so we have the integral 1 to e 2 pi x cubed natural log of x squared dx. Okay, we can work with this. We can work with this. There's definitely things we can do here. What do we do? All right, what's the right technique? Well, we definitely know it's not trig. But we see like, log. Ugh. I don't want to integrate log. So we say, well, there's a technique that says you don't have to integrate something. You can kind of differentiate it, and hopefully it gets simpler. So we're going to be doing by parts. And looking at this, we're going to say, okay, let's make the part that's hard to integrate, let's make that our thing we differentiate. So the log of x quantity squared, that's our u, which means that the other part, the x cubed, is going to be the thing we integrate. So this x cubed dx, that is going to be our dv. All right, so let's make some notes to the side here. So dv is x cubed dx, which means that if I want v, I integrate 1/4 x to the 4th. And on the other hand, we have u is the natural log of x quantity squared. So du, okay, we've got to do chain rule. 2 comes down times the natural log of x times the derivative of natural log of x, which is 1/x dx. All right, so now with all of that, we can update. So we get, this is the integral. Actually, it's not the integral. We're going to do our uv, 1/4 x to the 4th times natural log of x quantity squared. Evaluate that from 1 to e. It's a definite integral. Got to do evaluation. Minus the integral v du. The bounds, by the way, still the same, 1 to e. So let's see, what can we do? We'll just multiply them here. So we have a 4th times 2 makes a 1/2. And then we have the x to the 4th times 1/x, make that an x cubed. And then we have a natural log of x and dx. And before you jump on me and say, aha, Steve, you forgot something, I did, but I can still claim I hadn't forgotten it yet because I was still writing stuff down. What has not been written down yet? The 2 pi. Don't forget those constants. Oh, yes, you can't forget those constants. They're still there, always there. You could say that they're constantly there. So be careful. Be the right amount of careful with your constants. All right. So let's do some evaluation. Log of 1 is 0. Nice. Log of e is 1. All right, we'll even write that down. Log of 1 is 0. Log of e is 1. Just make some notes here. Okay, and so what's left? Well, we have the 2 divided by 4 makes a pi over 2 e to the 4th power. Okay, so that's that part. And then here, minus, and we can bring the half out, so minus pi, and now that accounts for, just to be clear, because after that we have that and that accounted for. Okay, and then we need to do this again. Okay, so round 2. Well, last time we picked the log and took rid of that. So stick with it. Once you make a choice, you got to be consistent. You can't change your mind later. You know, you have to stick it out. And unless it's hopeless, then you go back to the beginning and start over with a different choice. But all right, so we have the similar thing. U is log of x, and dv is x cubed dx. And you're like, didn't we just do that? Actually, not really, because notice this is actually a simpler integral. This has log of x quantity squared, and this is log of x. Simpler, right? Log of x is no longer squared. So that gives us optimism that we're heading in the right direction. Well, we still have our dv is x cubed dx, meaning v is 1/4 x to the 4th. And, all right, and then u is our natural log of x, meaning that du is 1/x dx. Okay, so what do we have? Well, we have our uv, 1/4 x to the 4th times natural log of x. Evaluate 1 to e, minus the integral, bounds are still there, definite integral, of v du. So 1/4 x to the 4th times 1/x. So that's a 1/4 x cubed. And see how we went log of x squared, log of x, no logs. So every time we did integration by parts, we sort of got simpler and simpler. And that's a good sign. It's a sign we're doing things well. And all right, so let's catch up on our evaluation. So we have our pi over 2, e to the 4th. Now, when we plug in 1, log of 1 is 0. Plug in e, log of e is 1. And so we have e to the 4th times the 4th times this minus pi. So that's minus pi over 4 e to the 4th. Okay, minus makes a plus pi. And then we have 1/4. Integral of x cubed will bring another 4 down. So this will be a 1/16. And then we have x to the 4th. I was starting to evaluate, but I shouldn't have. So we have to evaluate from 1 to e. Okay, and okay, pi over 2, subtract pi over 4. 2 pi over 4, subtract pi over 4, means pi over 4 e to the 4th. Plus, okay, plug in e, pi over 16 e to the 4th. Okay, that's going to be interesting. We'll put those together in a second. And then plug in 1. Now here, doesn't go away. And what do we have? Subtract pi over 16. Well, pi over 4 is also known as 4 pi over 16. So we can combine it with that pi over 16 to make it 5 pi over 16 e to the 4th minus pi over 16. And there we go. Oh, whew. Wow. Wow. What an answer. What an answer. All right. Well, what did we do? we said, what's our region? How should we break it up? We used our function to say, break it up in terms of x. Figured out we should use the shell method. Set up our shell method. And then he did integration by parts twice. And carefully, use your parentheses to help make sure you distribute. Don't forget to bring your constants along. And take your time. Take your time. Be consistent in your choices. You can do this. You can do this. You are amazing. I believe in you. Keep working, and it's going to become second nature. And then it becomes fun. It's a game, and it's a game you can win. Thanks for joining me. Keep working, and I hope you can join me again. Bye.